Now, what is there in a 12 pulse transformer? So, the circuit arrangement of a 12 pulse transformer is shown here. You have one secondary, one primary and two secondaries here, one secondary in star and another secondary in delta connection. Okay. So, the primary and secondary, the star star connection has a turns ratio 1:1, and this star and delta has a turns ratio of 1:√3. Okay. Now, in case of a 12 pulse transformer, in this fundamental cycle 0 to 2 pi here, now we get 12 pulses in this fundamental cycle or 12 number of lobes. Here as you can see, there are 12 lobes here. In a 6 pulse transformer we had 6 lobes, and now in a 12 pulse transformer we have 12 lobes. And why these 12 lobes are happening? Because there are two diode bridge rectifiers now, they are series connected. Okay. So, this is the plus. So, you can, so this is the plus and minus, and this is the plus and minus, and they are series connected. Okay. The diode bridge rectifier outputs. So, now we have a 12 pulse waveform at the output. Now, when we have a 12 pulse rectifier, then of course, the output DC ripple is improved, because you see here that we have now 12 pulses. So, we have this the width of one lobe is 30 degree, this is 360 degree divided by 12. So, if it is 30 degree, then if this is 1, then this value will be cos of 15 degree or cos pi by 12. So, this is what is written here, cos pi by 12, this is 1, this is cos pi by 12, and this is 0.96. So, the output ripple in the output voltage is now only about 4%. Okay. Earlier we had seen that the ripple in the output voltage was about 14%. So, the 12 pulse rectifiers were used in earlier days, or even now today also 12 pulse rectifiers are used, because it gives a substantial improvement on the output voltage ripple. Okay. But there is one more benefit, that is what we will focus now, is the improvement in the input current. Okay. So, we would like to see how a 12 pulse rectifier or a 12 pulse rectifier from a 12 pulse transformer, how does it improve the input current harmonics. Okay. So, that is what we are saying, what is the effect on the input current distortion. Okay. We are not focusing on the output voltage here. So, in order to understand what is the input current, so we see we can make the MMF balance on the transformer. So, we have this one, this has a 1:1 turns ratio, and this transformer has 1:√3 turns ratio. Okay. So, therefore, I capital A here is the sum of contribution from these two transformers. Okay. So, therefore, I capital A is IAS plus √3 times IA dash. Okay. So, this has a turns ratio of this one. So, we can also write here. So, this is coming from the star, this one is coming from the star, that is this contribution. So, I capital A is this IAS, and this contribution is coming from the delta. Okay. This is coming from the delta transformer. So, we can say that √3 into IA dash is equal to 1 into IA. Okay. From the for the delta part only, we can write this relationship, from which we have written this one here √3 IA dash, because the turns ratio here is √3. So, √3 times this current. is this one. Similarly, we can also write IB and IC, which is following the same procedure. Okay. Now, then the question comes up, what are the values of IA dash, IB dash and IC dash? Okay. Now, the output current of the delta transformer IAD, so we can write the KCL at this junction. So, IAD is nothing but IA dash minus IC dash, that is what I have written here. In a similar way, we can write IBD and ICD as IBD as IB dash minus IA dash, that is writing the KCL at these 3 nodes. Okay. So, these are the 3 equations here. So, subtracting 2 from 1, I can find out IAD minus IABD is like this, and for a balanced system, if we assume that IA dash plus IB dash plus IC dash is equal to 0, then we can substitute it back, and thereafter we get an expression of IA dash is equal to IAD minus IBD divided by 3. Okay. So, we are getting the current IA dash in terms of these line currents. The phase currents in the delta are obtained as a function of these 2 line currents. So, IA dash is equal to IAD minus IBD divided by 3. Okay. And by symmetry, we can also write IB dash is IBD minus ICD by 3 and IC dash ICD minus IAD divided by 3. Okay. Now, let us look into what are IAS and IAD waveforms. Okay. This is important to understand the waveform of I capital A. We are trying to get the waveform of I capital A. Okay. We have found one relationship, this is this one, I capital A is the contribution of the star and the delta, that is first, and then we have also found out IA dash is a function of these IAD, IBD, ICD. Now, we would like to plot what is the waveform of IAD and IAS. Okay. This current and this current, how will it look like? So, we have seen, so this is what we have already studied. We have said, and also from your basic power electronics, you can recollect that the current IAS here is a quasi square wave, okay, which we have just also said in the few slides back. It is a quasi square wave like this here, that is IAS, right. Now, IAD is also a quasi square wave. Okay. This is also feeding a diode bridge 6 pulse rectifier here. This is a 6 pulse, this is another 6 pulse. IAD is also like this, but IAD is phase shifted by 30 degree. Why? Because the line voltage of the delta is same as the phase voltage, there is no phase shift, whereas the line voltage in a star connection is 30 degree leading to the phase voltage. Okay. So, for that reason, the sequence of conduction of the diodes in this rectifier will be 30 degree phase shifted, and hence the current waveform IAD will be exactly similar to IAS, but it will be 30 degree phase shifted because of how the diodes are conducting in the upper rectifier and the lower rectifier, because this voltage and this voltage has a 30 degree phase shift between them. So, therefore, IAS and IAD will have a 30 degree phase shift in it. So, if IAD is obtained, I can also draw IBD, because IBD is 120 degree lagging to IAD. So, therefore, I can, so this is my IAD, and so IBD is 120 degree. So, you can see here this is 120 degree or 2 pi by 3 shifted, IBD is 2 pi by 3 shifted on this side. So, once we get IAD and IBD, we have seen IA dash can be readily obtained, as IAD minus IBD by 3. So, IAD minus IBD by 3. So, we get IA dash here, okay, which is something like this here. Okay. So, this is the phase current in the delta. Okay. So, this is the IA dash here, this is the phase current in the delta. So, we have IAS here and we have IA dash here. So, these two waveforms we have now obtained. Okay. Now, we would like to know what is I capital A, for which we use this relationship here, IAS and IA dash. So, both of them we have obtained. Now, we have to multiply IA dash by root 3 and add it with IAS, right. So, if we do that, if we multiply this waveform by root 3 and add it to this waveform, you can do it yourself and you will find that I capital A has a waveform like this. Okay. You can do this exercise yourself. So, I capital A waveform is something like this. Okay. You can see that I capital A is distinctly different from IAS. Okay. So, if we had only a 6 pulse rectifier with 1:1 transformer, then I capital A with both sides in star, for example, then I capital A and I small a s, these two would have been identical, right. But now, in the presence of this star delta transformer, we see that IAS waveform and I capital A waveform is distinctly different. Okay. I capital A waveform has more number of steps like this with these values here. Okay. So, let us now analyze this waveform and find out what are the harmonics. Note that we have been doing this exercise to find out that whether we will get any improvement in the input current waveform I capital A. Okay. Really, do we really get any improvement? That is what we are trying to find out. So, if we see this waveform and we do a Fourier analysis of this. Okay. So, how can we do the Fourier analysis? We can do it, of course, we can do it by the symmetries and all, but we can also do it slightly intelligent way by splitting this waveform into 3 parts. Okay. So, one part is this one here, okay. The other part is this one and the third part is this one. So, how are we getting this? So, the first part, this one is coming from this part of the waveform. Okay. So, this part of the waveform like this to this part of the waveform. So, this is the first part of the waveform, this part of the waveform is coming here. Okay. So, you can see the magnitude. So, this waveform is a square wave with amplitude of ID by root 3 and minus ID by root 3 here. So, this is the waveform which is coming here. So, this is the first part of the waveform. What is the second part of the waveform? The second part of the waveform is this part of the waveform. And this part here. So, it is like this here, here and here. So, this part of the waveform is what is drawn here. Okay. So, this is the second part. So, the amplitude of this one is 1 plus. So, the amplitude is 1 plus 1 by root 3 minus 1 by root 3, and so the amplitude is 1 here. So, because it starts from 1 by root 3, so the amplitude is 1 plus 1 by root 3 minus 1 by root 3, and so the amplitude is 1. So, that is what we have said, it is a quasi square wave, starts from pi by 6 and then it has an amplitude of 1 here. Okay. So, this is the second part of the waveform. What is the third part of the waveform? The third part of the waveform is this part here. This part of the waveform, which is again drawn here. Okay. This is the third part of the waveform, right. So, we can split the whole waveform into 3 parts, okay. And when we can quickly apply the formula that we had derived a little bit earlier. What we had derived? We had derived that f t is okay, let me go back and check this formula. How did we write that formula? So, we had seen that f t is equal to 4 I by n pi cos n alpha sin n omega t. That was the generalized expression for an angle of alpha quasi square wave with alpha and pi minus alpha here. So, therefore, we can write the Fourier series expansion of this waveform and this waveform and this waveform, and then just add it up. Okay. So, this waveform will have, so the first waveform here, so let me rub this off, sorry. So, let me rub this off. So, the first waveform here has alpha equal to 0 degree and its magnitude will be 4 I d by root 3 n pi. So, this is the first expression, okay, alpha is equal to 0 degree, right. For the second one, what we find that the alpha is equal to pi by 6 and its magnitude is 1. So, 4 I d by n pi cos n pi by 6 sin n omega t. So, this is the this is for the second waveform, f to t is for the second waveform here. And what is about the third one? For the third one, alpha is equal to pi by 3. So, cos n pi by alpha, so cos n pi by 3, and the magnitude is 4 I d by root 3 n pi here. So, 4 I d by root 3 n pi cos n pi by 3 sin n omega t, right. So, if we add all these 3 together, then so we get the total f t of the whole waveform. So, f t is f 1 t plus f 2 t plus f 3 t, and so we write the total expression here of f t, okay, 4 I d by n pi and this big expression here. So, if we put now n equal to 1 in this expression, we will get the fundamental component in the input current waveform I capital A. Okay. So, n equal to 1, so we get this is the magnitude of the fundamental. Okay. For n equal to 5, you will see that f t is equal to 0, and that is true also for n equal to 7, f t will be equal to 0 if you put n equal to 5 and 7 in this expression. Okay. And not only 5 and 7, but any 6n plus minus 1 where n is an integer will give the value of f t to be 0. You can put it and check it. So, we see that for any 6n plus minus 1 harmonics, so the input current cannot have any 6n plus minus 1 harmonics. So, n equal to 5, n equal to 7, where n is equal to odd, for so n equal to 17 and 19, and then again n equal to 29 and 31, these harmonics will all be absent. Okay. Now, for n equal to 11, if you put for n equal to 11, you will get again another value. So, this means that the harmonics present in the input current are at 11, 13, 23, 25 and in general 12 and plus minus 1 harmonics are present. Okay. So, this 5th, 7th harmonics are totally absent. This has a substantial effect on the input current distortion. Okay. As we had said earlier, 5th and 7th harmonics have the maximum impact because they are close to the fundamental. Okay. Now, in this case we see that the 5th and 7th harmonics are gone, right. Also the third order harmonics are also gone. So, third n equal to 3, if you put n equal to 3, that will also come out to be 0. So, therefore, n equal to 3, 5, 7, 9, all these 4 harmonics are gone in the input current waveform and the first harmonic that comes is at n equal to 11. Okay. And then n equal to 11 and 13 and then it goes to n equal to 23 and 25 like that, 35 and 37, 47 and 49 like that. So, in general 12 n plus minus 1 harmonics are present in the input current. So, this substantially improves the input current waveform profile. Okay. Now, note that this harmonic cancellation in the input current is occurring because of the cancellation of the corresponding harmonic flux in the transformer core. Both the star and the delta windings are carrying the harmonic currents, okay, on the secondary side of the transformer. What happens is actually the cancellation of the harmonic fluxes in the core of the transformer. This you should understand. Okay, that is why the input current does not have the 5th and 7th harmonics. Okay. So, this is where we have shown the waveforms of IAS and IAD and then you can see the harmonics are present in the star and delta waveforms, that is what it is shown here, but in I capital A, that is the primary input current, the harmonics are 11th and 13th of that magnitude. Next we will see how can the harmonics be further improved. Okay. How can the harmonics be further improved? So, we can use in a similar way 18 pulse, 24 pulse or 48 pulse transformers. Okay. Now, for getting this higher pulse number, so as we go to the higher pulses, for example, if we go to a 24 pulse transformer, then the first band of harmonics will reside at 24 n plus minus 1. So, 23rd and 25th is where the first harmonics will reside. All other harmonics before 23rd will be totally absent. So, that is an advantage in terms of the input current quality. Of course, it is a disadvantage in terms of the complexity of the transformer. There is always a trade off, okay, between what is the how much improvement in harmonics we want to get and how much complex we would like to make our converter along with the transformer. Okay. So, for getting these higher pulse numbers, we can use the zigzag transformer or extended delta transformer. Okay. Now, let me, before I proceed on the zigzag transformer, let me see or let me show you how the zigzag transformers or these multi-pulse transformers can be used in a suppose a cascaded edge bridge converter. So, we had seen that cascaded edge bridge converters had a large number of DC sources, isolated DC sources, we required them, isolated DC sources here. Now, these DC sources can be are of course fed from a diode 3-phase diode bridge rectifiers like this here. So, suppose we are showing here the 5 cell version of the cascaded edge bridge. So, if we have 5 cells here, all these 5 cells have an input rectifier, a DC bus, and then we have H bridges here, and they are connected on the AC side here. Now, what happens at the input side? At the input side, we can use a multi-pulse transformer. Okay. We can use a multi-pulse transformer. So, if we use such a multi-pulse transformer, then we can on the input side of this, the current drawn from the input side, that is this current here, this current will be highly sinusoidal waveform. Okay. So, this is for example, like this is 5 cells are there. So, the input current will be well below the standards IEEE or IEC standards, harmonic distortion standards, THD will be way below. So, the in this cascaded edge bridge converter, we had said that we require isolated DC sources. That was a disadvantage. We require isolated DC sources. So, we need a transformer with several secondaries, that was a disadvantage. However, this advantage to some extent can be used to our advantage by making a multi-pulse transformer here. Okay. So, if we use such a thing, then the input current distortion can be substantially reduced. Okay. So, in a similar way, the NPC, the neutral point clamp converter, we had seen that there was a DC bus, and this DC bus can also be created from a star delta transformer. Okay. So, in NPC, so we had seen that in NPC we had this DC bus. So, this was going to the 4 switch. So, this was the NPC converter. So, we can make a star delta transformer, okay, with rectifiers, and can make a connection like this, such that the input current, this current here, has substantially lower harmonics. Okay. This is possible. Okay. So, when we talk about this higher pulse transformers, we usually talk about zigzag or extended delta connections. So, we continue with the multi-pulse transformer. So, today's discussion will be on zigzag transformer and how the zigzag transformer helps in improves the input current harmonics. So, that is what we will study. Now, here we see the zigzag transformer. There is, you can see here, there is a, suppose there is a star connected primary and there is secondary 3 phase, but in this secondary winding, in this secondary side of the transformer, the windings are split into 2 parts. Okay. So, for example, you can see here that this is the R phase winding, and the R phase winding is split into 2 parts, and we can say that their turns ratio are K1 and K2. If this number of turns here is 1, we can say that this turns ratio is K1 and this is a K2, okay, of the R phase. So, we have now physically split the R phase winding into 2 parts having turns equal to K1 and K2. Similarly, we have also split the B phase and C phase into 2 parts having K1 and K2. We can do this always because these windings are on a core, okay, and we can have 2 windings like having K1 turns and K2 turns on the same limb. So, they are basically linking the same flux. So, we can draw then the diagram like this. Okay. So, in order to make a zigzag transformer, we subsequently interconnect these windings, but slightly in a different fashion. Okay. How do we connect it? See here, we first say take this winding K 1, this winding here K 1 and put it here like this K 1. Similarly, we take this winding and we draw it like here, what I have drawn here, and we take this winding, the blue one, and draw it here, and then we connect the one side of the winding to form the star point here. Okay. So, we have taken this winding, this winding, so this winding and this winding, and we have formed this one and this one. Okay. Now, we take, for example, this winding of the C phase. We take this winding here and put it here, okay, and we connect them together. So, we have connected them together here. Okay. So, this here, this is having K 2, this comes here and is connected to the K 1 windings, K 1 turns of the A phase winding, and K 2 of the C phase winding is connected. Similarly, you can take this winding and we can connect it here like this, and we can take the B phase, this K 2 winding, and can put it here, right. So, once we do this, what happens? What we see then is that the voltage produced. So, if we take the voltage from this point here and here and here, okay, if we extract the voltage from these points, then what happens? There is a particular phase shift between the input side voltage and the output voltage. For example, this is O point and this is also O point, O small a and O capital A here. Okay. Suppose in the primary side we have a O small a, this is the primary voltage, and O capital A, this is the secondary voltage. Okay. Once we have already interconnected. So, this O capital A, this voltage will have a phase shift between them. Suppose we make O small a, this magnitude is equal to O capital A, right. Suppose we make the voltages equal, but then we see that there is a phase shift between the voltages of O small a and O capital A. Okay. And this is what the zigzag transformer does. And how much is this phase shift? This phase shift here is denoted by theta here. Okay. This is the phase shift, and you can immediately recognize that this phase shift is dependent on the values of K 1 and K 2, right. So, by changing the values of K 1 and K 2, the angle theta here. So, this is a triangle here with having K 1 and K 2, and I can assume, for example, that this length is 1, okay, where this length is also can be 1 or can be anything else also, so, depending on the turns ratio we want or the voltage ratio we want from the primary to the secondary side. So, therefore, this angle theta can be changed by changing the values of K 1 and K 2. Okay. So, what does that mean? If we split, so how did K1 and K2 originate? Because we had split the winding into K1 and K2 parts. Okay. So, therefore, by changing the ratio of K1 and K2, I can change the value of theta here. Okay. So, this makes an advantage, or this creates an advantage, that this theta value is kind of like adjustable depending on the values of K1 and K2 chosen, right. So, this is a zigzag transformer. Okay. So, this is the star side and this is the zigzag transformer connection and the corresponding phasor diagram here. Okay. So, the amount of phase shift on the output of the zigzag transformer can be controlled or can be adjusted by changing the values of K1 and K2. Okay. So, this is what is also shown here mathematically. So, you can see here we have seen this diagram. We have seen this diagram. So, this is O, A, B, C. So, you can find out the mathematical relation between K1, K2 and VA. For example, this is the output phase voltage of the zigzag transformer. So, then you can see K1 by sin pi by 3. So, this is the triangle, this angle is theta, this angle is 2 pi by 3 or 120 degrees, and then this is 60 degree minus theta. Okay. And these sides are K1, K2, and this side suppose we define as VA. Okay. That is the required line voltage, required phase voltage magnitude. So, therefore, we can write K1 by sin pi by 3 minus theta is equal to K2 by sin pi by 3, which is equal to, no, there is a small mistake here. So, we should write it K1 by sin pi by 3 minus theta is equal to K2 by sin theta. So, this is not pi by 3, this is K2 by sin theta. Okay. So, there is a mistake here. So, K2 by sin theta, which is equal to VA by sin 2 pi by 3. Okay. So, now we can find out what is the required K1 and K2 here in terms of VA. And so, suppose we can have, suppose we want a zigzag transformer with theta equal to 15 degree. Okay. Then we can find out what is the required value of K1 and K2. Okay. If we want a theta equal to 7.5 degree, then we can accordingly choose K1, K2. Okay. So, we will split the phase winding into two parts. Okay. This is the K1 and K2 parts. So, how do we actually do it in a transformer? It is very simple actually. So, here you can see that is the R phase winding, the total number of turns is K1 plus K2, which we have split into two parts, K1 and K2. Okay. And then we are now interconnecting. So, we have done this K1 and K2 for R phase, for B phase, and for the three phases here, A, B, C phases. Now, we can interconnect as per this diagram here, and then we will see that we are getting the required phase shift between the primary and secondary side of the transformer. Okay. So, this is the secondary side, we have not shown the primary side. This is the secondary winding connections, which is connected now in a zigzag fashion. Okay. So, this is how we actually do the circuit, or we actually do the connection. So, for n pulse transformer, now coming back, so we were talking about the 12 pulse transformer. Now, in case of a zigzag transformer, suppose we want to get a 24 pulse transformer, or in general we can say that if we require an n pulse transformer, the phase shift required in the secondary output of the zigzag transformer is 360 degree by n. So, for example, for a 24 pulse zigzag transformer, the phase shift required is 15 degree. For a 48 pulse zigzag transformer, the phase shift required will be 7.5 degree, that is 360 degree divided by n. Okay. And the number of rectifiers to be used is n by 6. Okay. For 24 pulse zigzag transformer, the number of rectifiers is 4. So, let me show you a connection here. You see here a 24 pulse zigzag transformer connection. So, here you can see that the primary is connected in star and there are 4 secondaries. Okay. Why 4 secondaries? Because for a 24 pulse we require 4 secondaries, each rectifier gives 6 pulse. So, that with these 4 secondaries, of course, we have 4 rectifiers connected here, we have not shown that. So, if you see here, these outputs are connected to rectifier. Okay. This output is again connected to a rectifier. Similarly, there is a rectifier and there is a rectifier here. So, there are 4 sets of rectifiers here, right, and these 4 sets of rectifiers, they will be series connected. Okay. So, that we get 24 pulse voltage output here. Okay. So, each rectifier gives 6 pulse and 4 rectifiers will give us 24 pulse rectifier output, right. And so, what will be the phase shift angle? What will be the phase shift angle? The phase shift angle will be 15 degrees. Okay. So, we can have the star, we can assume that star as a 0 degree. So, we can have one star connected transformer secondary having a 0 degree phase shift. Then we will have minus 15 degree, plus 15 degree or 30 degree. Of course, 30 degree we can have with the delta. Okay. So, we need 4 transformers whose output voltages are phase shifted by 15 degrees. So, one transformer is the star which gives a 0 degree phase shift, one can be a delta which gives us a 30 degree phase shift, but we need 2 more which we will get from 2 zigzag transformers. One gives us a 15 degree phase shift, one gives us minus 15 degree phase shift. Okay. In this way, we will be able to arrange for a 24 pulse transformer rectifier arrangement. So, what is the advantage of the 24 pulse? The advantage is that this current, input current, will have harmonics. The first harmonic will come at 23rd harmonic, 23rd, 25th, 47th, 49th, like that. No other harmonics will come on the input side, input current. Okay. Another way of, so there may be multiple ways of generating the 24 pulse. So, you can have the primary connected at 0 degree, you can also have the 4 zigzag transformers on the secondary instead of 2 zigzag as I have shown here. So, if you have 4 zigzag transformers on the secondary, you can have 22.5, sorry 22.5, 7.5, minus 7.5 and minus 22.5 degree angles. Note that the difference is 15 degree between these outputs. Okay. But this arrangement is more symmetric as compared to this. Okay. This is more symmetric. So, it actually the stress on the transformer for a more symmetric arrangement is less. Okay. In particular, during short circuit condition of the transformer, there is a stress on the transformer, and due to the short circuit current, and this the mechanical stress on the windings can be more symmetric if we have a more symmetric output on the zigzag transformer. Okay. So, preferably this connection may be used. Okay. So, in a similar way we can also have a 30 pulse zigzag transformer. So, with 30 pulse zigzag transformer the phase shift required is 360 degree by 30. So, 12 degree, and how many we will need, how many rectified zigzag transformer or how many rectified transformer, we need 5, because each rectifier produces 6 pulse. So, for 30 pulse we will require 5 such sets. So, then you can have different types of arrangement like 0 degree here, then you can have 6 degree, minus 6 degree, minus 18 degree, 18 degree and 30 degree. Okay. So, 12 degree gap between them, or you can have 0 degree and 0 degree like this, you can have minus 12, minus 24 or plus 12 and 24 degrees. Okay. So, this is how the zigzag transformer can be helpful for creating the phase shifts, right. So, it is like the construction is quite simple, because it is only a matter of changing the values of k1 and k2 in order to change these angles. So, this angle is for example 24, and this angle this angle is minus 24 degrees, and this angle can be minus 12 degrees, and you can see from the diagram here that the k1 and k2 ratios are changing. Okay. Here we have changed the sequence also 12 degree, and so by observing this one you will be able to find out how much phase shift is required. Now, we will talk about another transformer which can also produce this phase shift, which is the extended delta transformer. Okay. So, the in extended delta transformer also the secondary winding is again split into two parts, k1 and k2, and subsequently they are interconnected. In case of a zigzag transformer, this interconnection happened with one side connected in star. In an extended delta, this other possibility comes up, and you can see here this is the secondary winding. Again you have a k1 and k2 split, that is blue colored, this is the winding, it is split into k1 and k2 parts. This one is split into k1 and k2 parts, and this one is also split into k1 and k2 parts. And now, if we take, and so the connection is like, it is made like this here. So, this phase comes and connects here, this phase comes and connects here. So, then again we find that the theta angle between the voltage at point A and the voltage at small point A here, there is a phase shift between the primary and secondary side. Okay. And so, this theta angle can again be controlled by choosing values of k1 and k2 and changing the ratio. Okay. So, extended delta and zigzag are basically following the same principle, where we change the, where we split the windings into two parts k1 and k2 and then reconnect. Okay. So, you can find out similarly what is the values of k1 and k2, as you can see here. Again we can follow the sine formula and can find out what are the values of k1 and k2 required to produce the desirable phase shift. Okay. So, let us now see how this extended delta can be used in a CHB. Okay. You can see here in this 5 cell CHB we have 5 rectifiers here, 5 rectifiers, and these are supplied from the secondaries of this extended delta connected transformer. Okay. The primary may be in delta, may be in star. Okay. One advantage of having an extended delta is that if there is any unbalance, that unbalanced current can flow inside the delta. Okay. The third harmonic or triplet the 0 sequence current can flow inside the delta winding, but here you can see there are 5 windings 0 degree, minus 12 degree, minus 24, 12 and 24. Okay. So, this is one of the possibilities of making the connection of a cascaded edge bridge. So far we had not talked about the input side, now we are talking about what can be a possibility on the input side. The advantage of this is that the input current waveform which we will draw from here, this waveform will be having very less magnitude of harmonics. Okay. So, this is the extended delta connection. One practice question from the input current and its harmonic spectrum. Okay. We can do one practice problem from here. So, suppose there is a waveform which is shown by this diagram, okay, and suppose ID here in this waveform, this is the current drawn, okay, at the input side of the rectifier, and so suppose this ID is equal to 1, it may be 1 per unit. Okay. So, what is the peak of the 11th harmonic component magnitude in the input current? Okay. So, this is 1, yeah, it is per unit, although I have said it ampere. So, you can take any value, it may be 1, it may be 100 also, yeah. So, yeah, so it is in ampere. So, therefore, what is the 11th harmonic component? So, we had seen that the 11th harmonic component is 4 I d by n pi cos n alpha sin n omega t. We have derived it in the class, and where alpha is equal to pi by 6, okay, and n is equal to 11. Okay. So, we are trying to find out the 11th harmonic magnitude. So, this is the magnitude of the 11th harmonic, where alpha equal to pi by 6 and n equal to 11. So, therefore, substituting the values 4 I by 11 pi cos 11 pi by 6, which comes out to be 0.1 if you take I d equal to 1. Okay. If you take I d equal to 100, it will come out to be 10 or something like that. Yeah. So, this is the magnitude and you can find it out easily. Now, the second question is, what is the magnitude of the 28th harmonic component present in the waveform? Okay. So, when you calculate the 28th harmonic, you have to be careful and see, because this is an even harmonic. So, does even harmonic is present in the waveform? So, if you analyze this waveform, it has half wave symmetry, okay, f of omega t and f of omega t plus pi. Okay. So, f of omega t is equal to minus of f of omega t plus pi, okay, see here and see here. Okay. So, therefore, this waveform has half wave symmetry and therefore, even harmonics cannot be present, and so the 28th harmonic, the magnitude is 0. Okay. So, this is the answer, this 0 magnitude.